To push 5G technology boundaries, Qualcomm Technologies has been investing in building advanced end-to-end prototype implementations of upcoming 5G deployments and designs. This demonstration showcases the mobility and performance of 5G NR mmWave operating in a real-life environment. This over-the-air test network setup is located at our headquarters in San Diego, and it operates in the 28 GHz band with up to 800 MHz bandwidth. We have one 5G NR mmWave G-Node B and 3 remote radio heads, or RRHs. RRH1 is on top of a 7-story building, RRH2 is installed on a pole in the lawn area, and RRH3 is on top of a 3-story garage. We also have 3 mmWave repeaters that can extend coverage and improve performance. The 5G Next-Gen core network is inside our R&D building in proximity. Here is our mobile test device based on the Qualcomm Snapdragon 5G modem RF system. It has 3 antenna modules that help to overcome blockage and orientation change so that a user can have a uniform experience. The GUI outlines spectral efficiency or throughput, depending on the setting, for mmWave downlink and uplink, as well as the antenna module selection and the associated beam selected for the connection. In this video, we will compare the performance of 3 different 5G mmWave repeater implementations. A simple repeater amplifies and forwards the signal bidirectionally and is always active. A TDD-aware repeater amplifies and forwards unidirectionally and is active either in the uplink or downlink direction depending on the slot structure. A smart repeater is both TDD-aware and supports intelligent and dynamic beam management, delivering beamformed uplink and downlink based on the slot structure. In the first scenario, the repeater is placed in line of sight to RRH3, but the user moves along a path that does not have line of sight. Our test results show that all repeater configurations can provide significant improvement in coverage and user throughput, as well as out-to-in coverage. The smart repeater, however, can provide substantial gains over simple repeaters. In this scenario, we see a user is moving along a path away from RRH3, but she is in line of sight. As she moves away, the signal strength deteriorates due to path loss and foliage, and a repeater is deployed to further extend the line of sight coverage. All 3 types of repeaters can deliver adequate range extension, but a smart repeater can maximize coverage extension with better beam management. In this scenario, a user walks into a building through a glass door. The repeater can provide mmWave connectivity from the outdoor RRH3. While all repeater types can provide range extension, a simple repeater with a wide beam is a good solution in this application as it is the most cost-effective and simplest implementation. In this scenario, the indoor user continues to be served by the outdoor RRH as a repeater installed by the glass window overcomes both out-to-in and diffraction losses. In this case, a smart repeater can provide more robust mobile mmWave performance. Lastly, we are showcasing how repeaters can improve multi-user multiplexing performance. One user is served directly by the G-Node B, and the second is served by the repeater. The smart repeater delivers the best performance here with intelligent beamforming and reduced interference. In conclusion, we saw that 5G mmWave repeaters can cost-effectively improve coverage, mobility, robustness, and user experience for a wide range of deployment scenarios. We look forward to taking this technology from our test beds to real-life networks.
Adopting machine learning for wireless communication can deliver new benefits, and this demonstration showcases how it can enhance 5G mmWave system performance and efficiency. This is our mmWave OTA test network in San Diego. In this test, we have implemented machine learning-based beam prediction at the G-Node B, and we're comparing its results to traditional non-machine learning-based beam selection in our OTA network. Here, we see several charts on the right side of the screen. The first chart shows the signal strength captured from device reports and compares it to the ML prediction. You can see that they're very close to each other, thereby showing the accuracy of the prediction. The second chart shows the beam selection by the OTA system with and without machine learning. There are 8 possible beams to choose from, selected based on channel conditions. The teal line shows when they match, which is the desired outcome. The last chart is another representation of how well the beams matched. The diagonal line in teal is the desired outcome, and it shows the percentage of time matching is achieved for different beam selections, and the red combination represents mismatch. In conclusion, machine learning assisted beam prediction can reduce the communication overhead of the system, thereby increase the usable capacity and extend device battery life. As we've shown, there is still room for potential improvements for machine learning-based beam prediction, and we will continue to improve our algorithms in the months to come. So stay tuned for another update soon.